Students, good morning. Today I am going to solve a problem. The problem is carbon dioxide enters in an adiabatic compressor at 100 kilopascal and 250 degree Kelvin at a rate of 0.1 meter cube per second and leaves at 500 kilopascal. Carbon dioxide is assumed to be an ideal gas. Determine the work of compression per unit mass for reversible adiabatic compression. Given data are, take the index of adiabatic process gamma or heat capacity ratio gamma is equal to 1.4 and at a temperature of 250 degree Kelvin the density of carbon dioxide is found to be 2.136 kg per meter cube. Now I am going to solve the problem. The problem comes under the category of applications of thermodynamics to flow process. Application of thermodynamics to flow process, that too in compressor. Clear? Right. Initial condition P1 is equal to 500 kilopascal. Initial pressure 100 kilopascal, final pressure P2 is equal to 500 kilopascal. 500 kilopascal, and at a rate of volumetric flow rate is given. Volumetric flow rate is equal to 0.1 meter cube per second. Density data is given. Hence mass flow rate is equal to 0.1 meter cube divided by second into 2.136 kg per meter cube. Meter cube gets cancelled. So the mass flow rate is equal to 0.2136 kg per second. Volumetric flow rate is given. Mass flow rate is equal to volumetric flow rate into density. Volumetric flow rate into density. It gives mass flow rate. Okay. At a rate of 0.1 meter cube and leaves at 500 kilopascal. Okay. Initial temperature is 250 kilopascal. Degree Kelvin. And final temperature, it is not given in your question paper. Clear? Final temperature, you have to establish or determine the final temperature by using the pressure volume temperature relationship of an adiabatic process. For an adiabatic process, PV power gamma is equal to constant. PV power gamma minus 1 is equal to constant. T power gamma into P power 1 minus gamma is equal to constant. Therefore, T power gamma is equal to P power gamma minus 1. So, T is equal to P power gamma minus 1 divided by gamma. So, T2 divided by T1 is equal to P2 divided by P1 power gamma minus 1 divided by gamma. So, final temperature T2 is equal to T1 into P2 divided by P1 power gamma minus 1 divided by gamma. This is established by using temperature pressure relationship for an adiabatic process. Hence, now I am going to find T2. T2 is equal to T1 250 degree Kelvin into final pressure 500 kilopascal divided by initial pressure 100 kilopascal to the power of gamma minus 1 divided by gamma 1.4 minus 1 divided by 1.4. So the answer is 395.25 degree Kelvin. So final temperature was established. So initial temperature and final temperature are known. Initial pressure and final pressure are also known. Now I am going to determine the work of compression per unit mass for a reversible adiabatic compression. The reversible adiabatic compression process. minus Ws is equal to changes in enthalpy. Yes. This S stands for entropy. Entropy. Now entropy is constant because it is a reversible adiabatic compression. Adiabatic means there is no exchange of heat. There is no heat interaction between system and surrounding. Reversible means amount of work supplied to the compressor for compressed carbon dioxide from 100 kilopascal to 500 kilopascal. The amount of work is completely utilized. For a reversible process, changes in entropy is zero. Changes in entropy for a reversible process is equal to zero. Hence, this is isentropic process. Hence, this is called as isentropic process. This is shaft work. S stands for shaft work. This shaft work is called as isentropic work. Isentropic work. Clear? Isentropic work means minimum amount of work required for the compressor. Minimum amount of work required for the compressor to compress carbon dioxide from 100 kilopascal to 200 kilopascal. Hence, this work, shaft work is called as isentropic work. Okay. Now I am going to calculate the work done by the compressor. So Ws is equal to minus del Hs. Changes in enthalpy is nothing but Cp into dt. Cp into dt. Okay. Cp minus Cv is equal to R. Cp by Cv is equal to gamma, index of adiabatic process. So Cv is equal to R, Cp is equal to, I am going to cancel, I am going to bring this relation term in terms of Cp. So Cp divided by gamma is equal to Cv. Substitute this information here. So Cp minus Cp divided by gamma is equal to R. So Cp into gamma minus 1 divided by gamma is equal to R. So Cp is equal to R divided by R into gamma divided by gamma minus 1. Substitute in this information here. So minus of R into gamma divided by gamma minus 1. On differentiation, this becomes T2 minus T1. Clear? So this equation becomes gamma divided by gamma minus 1 into R into T1 minus T2. In order to eliminate this minus sign, T2 minus T1 becomes T1 minus T2. Now I am going to find the shaft work. W is equal to, S is equal to gamma 1.4 divided by 1.4 minus 1 into R 8.314 joules per mole degree Kelvin into initial temperature 250, final temperature 395.25 Kelvin. So Kelvin gets cancelled. The answer becomes joules per mole. The answer in terms of joules per mole. Okay. What's the answer? Ws is equal to minus 4226.65 joules per mole. So I am in need of amount of work done per unit mass. Hence I am going to divide this answer by molecular weight of carbon dioxide. So 44 gram per gram mole. Mole gets cancelled. The answer is 96.05 minus 96.05 joule per gram. This is the amount of work, minimum amount of work required to compress carbon dioxide from 100 kilopascal to 500 kilopascal per gram of carbon dioxide. This is the shaft work or isentropic work. This is method 1. This is the first method. Next method, answer Ws is equal to minus 96.05 joules per gram. Method 2. Ws is equal to gamma divided by gamma minus 1 into RT1 into 1 minus P2 divided by P1 power gamma minus 1 divided by gamma. This is the next equation to estimate the shaft work or isentropic work, method 2. So Ws is equal to 1.4 divided by 1.4 minus 1 into R 8.314 joule per mole degree Kelvin into initial temperature 250 degree Kelvin, Kelvin gets cancelled, into 1 minus 500 divided by 100 to the power of 1.4 minus 1 divided by 1.4. Clear? On substitution, this value becomes minus 4247 joule per mole. The answer becomes joule per mole. In order to cancel this mole term, you have to divide by molecular weight, gram per gram mole. So mole gets cancelled. The answer is minus 96.53 joules per gram. So this is the second method. Clear? The answer for second method is minus 96.53 joules per gram. This is method 2. Method 3. Method 3. Isentropic work is equal to gamma divided by gamma minus 1 into P1 V1 into 1 minus P2 divided by P1 power gamma minus 1 divided by gamma. Now I am going to substitute the values. Gamma 1.4 divided by 1.4 minus 1 into initial pressure 100 kilopascal, that is Pascal, into 1000. Kilopascal will be Pascal. 1 Pascal is equal to Newton per meter square. So 1 lakh Newton per meter square into V1. Instead of V1, I am going to substitute volumetric flow rate. Volumetric flow rate is nothing but 0.1 meter cube per second. Meter square, meter cube term. Cube divided Newton meter per second. That means joules per second. Answer becomes joules per second. Okay, what next? Into 1 minus 500 divided by 100 to the power of 1.4 minus 1 divided by 1.4. What is the answer? Minus 433.69 joules per second. Joules per second. In order to cancel this second term, I am going to multiply it by mass flow rate. Mass flow rate means 0.2136 kg per second. 0.2136 kg per second. Sorry, I am going to divide this information by mass flow rate. Joules per second into 0.2136 kg per second. Second term gets cancelled. The answer becomes, in order to cancel kg, 1 kg is equal to 1000 grams. Kg gets cancelled. The answer is minus 96.52 joules per gram. This is method 3. In either of the method, you can solve this problem. Minus 96.52 joules per gram. So in order to estimate the amount of work done or work required for the compressor to compress the gas from 100 kilopascal to 500 kilopascal under reversible adiabatic condition. Reversible adiabatic condition means it is an isentropic work. You can use 3 methods. Which one is fit to you, you can select the same. Okay, thank you.